All right, section 6.5, we are proving or using conditions of rhombuses, rectangles, and squares to prove rhombus, rectangle, or square. And so here we are reintroduced to the three theorems we learned earlier. That'll help us in this process. The first one saying that if the diagonals of a parallelogram are perpendicular, then you have a rhombus. The second one saying that if the diagonal of a parallelogram bisects opposite angles, then you have a rhombus. And the last one being that if the diagonals are equal in a parallelogram, then you have a rectangle. So you can use these three properties to help prove the three different shapes, or two different shapes. You can also use the basic properties of a rhombus, like all four sides congruent, as well as the basic properties of a rectangle, four right angles, as long as you know it's a parallelogram, to prove those shapes as well. And remember, the combination of a rhombus and rectangle's properties allow you to prove the square. So our first proof tells us that AD is 5, DC is 5, and ABCD is a parallelogram. We're asked to prove that ABCD is a rhombus. So with any proof, we're going to start off with a given statement. From here, we'll go ahead and apply something from the given. We know that AD and DC are equal. So since we know that AD and DC are equal, we can kind of make that connection here next to talk about congruence. So in our next step, we'll go ahead and say, that should be AD. AD is congruent to DC, or CD in this case, and we know that because equal measures means congruent segments. That's more or less just the definition of congruence. From there, we can also make the connection to the idea that we have a parallelogram. So since we're dealing with a parallelogram, we know that opposite sides should be equal. So AD should equal BC, AB should equal DC. So let's go ahead and talk about that. So BC equals AD and AB equals DC. And we know that by, in this case, properties of a parallelogram, where we've got opposite sides congruent. Keep in mind, we're trying to prove that all four sides are equal in this case. Right now, we've only shown that opposite sides are congruent. But if we look back at this step here in step 2, we know AD is congruent to DC. Well, AD is here, DC is here, so we can actually make the connection between those two. So what we can really show at this point is that AB is congruent to BC, CD is congruent to AD, just by connecting all of the different points. Because if these two are congruent to each other naturally, and they're each congruent to something different, then they all must be congruent to one another. And essentially, this is just a really spread out version of the transitive property, or you can go with the law or the rules of substitution. And so what we're able to show is that all four sides are the same measure because of that. And so since we can show that, we're now able to say that ABCD is a rhombus by definition of rhombus. Second proof, they're telling us that angle D is 90 and that ABCD is a parallelogram, and they've asked us to prove that ABCD is a rectangle. All right, so we start off every proof with the given, and the question is, where do we go from here? So if we know it's a parallelogram and we already know that angle D is 90, then we should recognize that consecutive angles in parallelograms are supplementary. So that means angle A has to be 90, as is angle C. So we can go that route. So angle A is 90 and angle C is 90. By properties of parallelogram, where consecutive angles are supplementary. We also know from a parallelogram that opposite angles are congruent. So if angle D is 90, angle B must be 90 as well. So we can say angle B is 90 degrees. And that's because we know opposite angles are congruent. So at this point, we have a parallelogram with four right angles, which is basically a rectangle, but I'm going to go for overkill here, and we're going to talk about the sides themselves. So AB is congruent to DC, AD is congruent to BC. So we have opposite sides congruent. And that right there, we know, is from, once again, opposite sides are congruent in a parallelogram, or definition of a parallelogram in this case. And so now we have all of the things showing us in the diagram that this is definitely a rectangle. So ABCD is a rectangle by definition of rectangle. In the next one, they tell us angle D is 90, AD is equal to AB, and ABCD is a parallelogram. And they want us this time to prove that we're dealing with a square. So chances are we're going to have to prove rhombus and rectangle all in the same proof before we get to the square. So first step, we start off with the given. From there, because they told us it's a parallelogram, we know that the opposite sides are congruent. So we're going to go ahead and talk about that. So AD is congruent to BC, AB is congruent to DC by property of parallelogram, or opposite sides congruent. But remember, in the given, we talked already about that AD was congruent to AB. But here in our diagram, we don't have a mark that way, so if we were to mark them so they matched, think about how everything would be related. Because of this statement here, after we showed the opposite sides are congruent, we actually showed that all of the sides are congruent. So at this point, we now know that ABCD is a rhombus by definition of a rhombus, because we showed 4 congruent sides. And we're kind of skipping a minor step here or there, but we're getting the general overall picture here. Next step, let's see if we can prove rectangle. Well, we know angle D is 90, so if angle D is 90, we know angle A and angle C also have to be 90. We also know that angle B would have to be 90 because A and C are consecutive, and B would be consecutive to the others. So at this point, we're able to show that the other 3 angles are 90 degrees by properties of a parallelogram, where we have consecutive angles supplementary. We could also say opposite angles congruent in this case as well. At that point, we've got 4 right angles, so that means we have ABCD is also a rectangle by definition of rectangle. And then because it is both a rhombus and a rectangle, we can say that ABCD is a square by definition of square. Here we're given that there's an isosceles trapezoid ABCD with AB congruent to DC. We want to prove that AC is congruent to BC, or DB, sorry. AC is congruent to DB. First step, starting off with the given. So given that we have diagonals in this isosceles trapezoid, I have a feeling we're going to be using triangle properties for the most part. But let's just start off by looking at something in this case that if we were trying to use triangle properties, that these 2 triangles would share. Well, the thing that they share would be side BC. So we can say that BC is congruent to BC by the reflexive property. Because ultimately we're trying to prove that the diagonals are equal, or in this case, the long sides of each of those individual triangles. So right now we've got, let's go ahead and erase the red here, make it a little easier to see. So right now we have 2 sides of both of the triangles, but we need a little bit more here. Well, if we think about it, we're dealing with an isosceles trapezoid. So we could also say that this angle here should be congruent to this angle here because they're base angles. So in this case, we're going to say ABC is congruent to DCB by definition of isosceles trapezoid. Those are our base angles. Those are congruent base angles. At that point, we can now state that the triangle ABC is congruent to triangle DCB, so those the two little smaller triangles I was talking about, and they're congruent in this case by side angle side. And then with that information, we can now make the connection between AC and DB, the diagonals, as being congruent through our CPCT, or corresponding parts of congruent triangles are congruent. And then the last one here, we're dealing with the last one here. We're dealing with a kite ABCD with segment AB congruent to AD and CB congruent to CD. We want to prove that angle B is congruent to angle D. So we start off with the given, and then the only way we're going to prove the congruent angles here is probably to use this, prove that this upper triangle is congruent to this lower triangle, kind of like what we did in the last proof, and then show something's congruent through CBCT. So let's just see if we can prove the two triangles congruent. Well, we've already got two pairs of sides, and we should be able to figure out that this side is congruent to itself through the reflexive property. So AC is congruent to AC through the reflexive property. Well, at that point, I now know that triangle ABC is congruent to ADC by side, side, side. And now that I have congruent triangles, I have more than enough ability to show that B and angle D are congruent. And I can prove that through CPCT, or corresponding parts of congruent triangles are congruent.